Today I will discuss about the design of some arithmetic circuit. First of all, I will discuss about the binary adder. Binary adder is an essential part of every computer because the micro operations addition and subtraction of two binary numbers stored in two registers are being performed by this unit. To implement the add micro operation with hardware, we need the registers that holds the data and the digital component that performs the arithmetic addition is the binary adder. So the digital circuit that forms the arithmetic sum of two bits and a previous carry is called full adder. And a binary adder is the digital circuit that generates the arithmetic sum of two binary numbers of any length. The binary adder is basically constructed with full adder. You are well acquainted with the circuit of full adder, so I am not discussing the full adder today. Binary adder are basically of two types. One is serial adder and the second one is parallel adder. The first one is serial adder and the second one is parallel adder. Okay, so these two are binary adder. So a serial adder is an adder which performs the addition of two binary numbers serially bit by bit starting with LSB. Okay, so when in case of serial adder, the operation is being done starting from LSB. So if I draw the circuit of the serial adder, the circuit will be like this. It will consist of a full adder and a D flip-flop. So this is a full adder. This is sum. This is C out or carry out, which is the input of the D flip-flop. This is the flip-flop input. This is output. Then D flip-flop. So this output will be feedback to the input of the full adder. So this is the stored carry that will be feedbacked. Stored carry feedbacked. These two are the input bit of the full adder. So AI and BI. I indicates the ith time. So in case of serial adder, the addition is being done serially. So first in one clock cycle, then the second clock cycle, like this, the addition is being performed. So a serial adder is an adder which performs the addition of two binary numbers serially bit by bit starting from LSB. That I have already mentioned. So here the addition will be done bit by bit. Remember, the addition will be done bit by bit starting from LSB. Okay. So if I want to add these two numbers, suppose I want to add these two numbers like this, 1 0 0 1 0. So if I want to add these two numbers, this is called the LSB and this is called MSB. So the starting will be with this LSB, the addition of with these two numbers, the addition will start. So addition of one bit position takes one clock cycle. So the addition of this bit position will take one clock cycle. So this will take one clock cycle. 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 So if there is 5 bit, then we need 5 clock cycle to add. Okay. So addition of one bit position takes one clock cycle. Remember, addition of one bit position takes one clock cycle. The circuit for the adder of serial adder will be like this. So it will consist of a full adder and one flip-flop. The operands are provided bit by bit starting from the LSB. So the operands at this will be bit by bit. Thus for an n-bit serial adder, n clock cycles are needed. As in the given example I have given that the number of bit is 5. So 5 clock cycles are needed. So in case of n bit numbers addition, if I want to add n bit numbers, then n clock cycles are needed. At each cycle, the carry produces by a bit position should be stored in the D flip-flop. So whenever the carry will produces, it will be stored in the D flip-flop and it is given as input during the next clock cycle through the carry in. This is the carry in circuit and through the carry in, this will be the input of the full adder. So here the D flip-flop, there will be a clock. So why there will be clock? At the first instant, the first clock cycle, we will add the LSB. Similarly, when the next clock cycle will be applied, then the next addition will be performed. So thus the Cout, it will get the Cout and give the result of the output resultant, and the second bit will be stored and that will be carry in of the full adder again. So at each clock cycle, the carry produced by a bit position should be stored in D flip-flop and it is given as input during the next clock cycle. So first of all, 1 0 will be added. So here the input will be 1 and 0. So in sum we will get 1 and in carry we will get 0. That means this Cout will come to the input in the next clock cycle. This is the carry. So in next clock cycle, when 1 0 will be added, this 0 will be added with that. Okay. So now then again the resultant will be 1. So when the resultant will be 1, this sum will be 1, carry out will be again 0. So then it will feed back to the input of the full adder to the next clock cycle. Thus, the serial adder is a sequential circuit. So, in case of, suppose I am giving the number, instead of this, suppose I am giving the number 1 1 1 1 0, here 1 1 1 1, like this. That means it needs 4 clock cycle. Okay. So first of all, when I am giving the input 0 1, it will start addition from this bit. When I will give 0 1, That means in sum I will get 1 and in carry it will be 0. Then it will be stored in the D flip-flop and will feed back to the input of the full adder. So 0 will be the input of the full adder, or carry in is 0. Now 1 will be added with it and C in is 0. So when 1 will be added, that means sum will be 0 and carry will be 1. So then Cout will be 1, and after the next clock cycle, that will be the input of the full adder. That means after second clock cycle, it will come to the next input, Cin. So 1 1 0 1, that means initially it will be 1, carry is 0. Similarly 1 1, that means sum will be 0, carry will be 1. This 1 will come to the input of the Cin, and when there is 1 1, this one will be added with this. So sum is 1, carry is 1. Okay. So again 1 1 1, that means sum is 1, carry is 1. Like this. So the serial adder we get, it is a sequential circuit, and the serial adder circuit is very small because here we need only one full adder and one D flip-flop. Hence, as the circuit is very small, it is very inexpensive circuit. As the number of it is very inexpensive irrespective of the number of bit, because the number of adder or number of flip-flop is not dependent on the input. Whether I have added with 5 bit, whether I have added with 4 bit or n bit, we need only one full adder and only one D flip-flop. But the disadvantage is that the circuit is very slow, since it takes n clock cycles for addition of 2 n-bit number. So if I want to add 10 bit, I need 10 clock cycle. If I want to add 50 bit, then I need 50 clock cycles. So the number of clock cycle depends on the number of bits. So we can say that the circuit of the serial adder is very slow. So this is the circuit of serial adder. Okay. So what is the advantage? The advantage is the circuit is small, hence it is very inexpensive irrespective of the number of bits added. But what is the disadvantage? The circuit is very slow, since it takes n clock cycles for addition of 2 n-bit numbers. Okay. So now I am doing the parallel adder. So first of all, I will do the parallel adder first. Then we will do first carry propagate adder. Or ripple carry adder. Carry propagate adder or ripple carry adder. This is the first one type of parallel adder, and the second one is carry look ahead adder. So carry propagate adder or ripple carry adder is used for addition of 2 n-bit numbers. So n full adders are required for this purpose. Suppose I want to add 4-bit number, then 2 4-bit number, then I will need 4 full adder. If I want to add n-bit number, 2 n-bit number, then we require n number of full adder. Okay. So suppose I am drawing the circuit of the full adder. So suppose this is my first full adder. Okay. Full adder 1. Next full adder 2. Full adder 2. Like this we can say that the last one is full adder n. Nth full adder. Full adder n. So first this is the S1. This I will get S2. Similarly here I will get Sn and the output will be carry out, that is Cn. In case of the first full adder there will be input Cin. Similarly this is the output C1. Similarly here we will get C2 like this. So what is the input in this case? The input is A1 B1. Here the input is A2 B2. Here the input will be AN BN. This will be BN, this is AN. So for addition of two n-bit numbers, n full adders are required. Each full adder's carry output will be the input of next higher bit full adder. This output will be the input of the next full adder. Similarly, this output will be the input of next full adder, like this. So, an n-bit carry propagate adder or ripple carry adder, that if we draw, the circuit will be like this. The block diagram will be like this. So, the addition time is decided by the delay introduced by the carry. So in worst case, the carry from the first full adder stage has to propagate through all the full adder stages. Therefore, the maximum propagation delay for n-bit carry propagate adder will be del multiplied by n, where del is the time delay for each full adder. Del is the time delay for each full adder stage, and n is the number of bits in each operand. Okay, so this is the circuit of the carry propagate adder or ripple carry adder. This is basically the block diagram. So here the adder is being a combinational circuit. This is faster than the serial adder. Serial adder was the sequential circuit, whereas the parallel adder is combinational circuit. So it is faster than the serial adder. In one clock period, all the bits of the two numbers will be added. No need to use much more clock cycle. In only one clock cycles, the clock period, all the bits of the two numbers will be added. So the addition delay becomes, what are the disadvantage of it? If the size of the numbers are to be added is increased, then the addition delay becomes large, because the delay is dependent on del into n. So if the number of bit is too large, then the addition time will be increased. So the hardware cost is more than the serial adder, because the number of full adders needed equal to the number of bits of the operands. So if we want to add 4 bit, then 4 number of full adder is required. If we want to add 8 bit, then 8 number of adder will be required. So n bit binary adder requires n full adder. The output of each full adder is connected to the input carry of the next order full adder. The n data bits of the A inputs come from one register, and then n data bits of the B inputs will come from another register. and the sum will be transferred to a third register. Suppose the data of A inputs come from one register, that is R1. Suppose the data from A, that is come from R1, and the data B inputs that come from another register, that is R2. In case of B, that will be R2. So the sum is transferred to a third register or one of the source register. It can be stored in R1 or R2. Okay. So this is all about the carry propagate adder or ripple carry adder. Now we will discuss about the carry look ahead adder. Okay. So the carry look ahead adder is basically it is a high speed adder. Okay. Now carry look ahead adder or CLA. So a carry look ahead adder is a high speed adder which adds two numbers without waiting for the carries from the previous stages. So in this case it is not dependent on the carry of the previous stages. As it is independent of the carry of the previous stages, in the CLA, carry inputs of all stages are generated simultaneously without using the carries from previous stages. So in the full adder, the carry output CI1, in case of full adder, if we write the carry output, this is the carry output, we can write it in this way: AI, BI plus AI plus BI into CI. So if we, this is the carry input and this is the carry output. AI, BI are the two numbers which is to be added. Then we can write the relation in this way. That means CI plus 1 equal to AI, BI plus AI plus BI into CI. So the result can be written as CI plus 1. The result can be written as CI plus 1 equal to GI plus PICI. Okay, so here GI equal to AIBI and PI equal to AI plus BI. Okay, so the function GI is called carry generate function. It is called carry generate function. Similarly, here PI is called carry propagate function. So GI is called carry generate function because I plus 1 is generated when both AI and BI are 1. It is called GI carry generated. So when AI and BI both are 1, because this is the AND operation. So when both are 1, then the input carry will be propagated to the next stage. So the function Pi is called carry propagate function. This is the carry propagate function. Since AI or BI is equal to 1, here this is the OR case. So if in case of Pi, carry propagate operation will be performed if AI or BI is 1. So here AI or BI equal to 1. And here AI and BI equal to 1. Okay. So in case of GI, that is called carry generate function, since carry Ci plus 1 is generated when both Ai and Bi are 1. The function Pi is called carry propagate function, since if Ai or Bi is a 1, then the input carry Ci is propagated to the next stage. So the basic adder for generating the sum Si, carry propagate Pi and carry generate Gi will be like this. This is the basic adder circuit. If we draw the basic adder circuit, it will be like this. This is the basic adder circuit. These are the input Ai, Bi. Similarly, Ci is another input. So here we will get the two function. One is carry generate Gi and another is carry propagate Pi. And here we are getting the summation bit, sum bit. That is the Si. So that is the circuit of basic adder. Okay. So now the sum bit Si equal to basically Ai XOR Bi XOR Ci. So for the implementation of one basic adder, two XOR gate and one AND gate and one OR gate are required, that we know already. So here if we want to design 4-bit carry look ahead adder circuit, here I am just generalize the carry look ahead adder circuit. So now I want to build 4-bit carry look ahead adder circuit. Okay. So next, now we want to design 4-bit carry look ahead adder circuit. So here for 4 carries C1, C2, C3, C4 will be generated. So first if we write the equation Ci plus 1 equal to Gi plus PiCi, and in place of Ci plus 1, if I put here C1, it will be G0 plus P0 C0. Okay. Similarly, in case of C2, we will write G1 plus P1 C1. So what is C1? What is C1? C1 is basically G0 plus P0 C0. So G1 plus P1 G0 plus P0 C0. Okay. So here when I am getting the C3, so here before this I can do Gi, Pi, G0 plus P1, P0, C0. Now I am doing C3, that is nothing but G2 plus P2, C2. So it is nothing but G2 plus P2. In case of C2, I am writing here P, this is P1. So P1 G0 plus P1 P0 C0. Okay. So now I will write the equation like this: G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. Now for C4 I am writing G3 plus P3 C3. Here G3 plus P3. In case of C3, I am putting here G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. Okay. So now we will get the equation like this: G3 plus P3 G2 Now P3, P2, G1 plus P3, P2, P1, G0 plus P3, P2, P1, P0, C0. This is nothing but P2. This is nothing but P2. Okay. So these are the equation. So here if we write the equation number, if we write here, this is the equation number 1. If we write it at equation number 1, G0 P0, this is the equation number 2. Then G1 P1 G0 P2, this is the equation number 3. Then this will be the equation number 4. So equation number 5 will be this. Last one is the equation number 5. So the equation number 2, 3, 4, 5 suggests that C1, C2, C3, C4 can be generated directly from C0. It is independent on C1, C2 like this. The output is only dependent on C0, the initial carry. For this reason, we can say that the equation are called the carry look ahead generation. And the 4-bit carry look ahead at a circuit, if I draw the circuit that is dependent on only C0. So if we draw the carry look ahead generator, I am drawing 4-bit carry look ahead adder circuit. For these 4 basic adder will be needed. So first of all, it is A0 B0. This is A1 B1. This is A2 B2. And this is A3 B3. And in this is the sum S3, S2, S1, S0. Now this is P0, this is G0. Similarly here it will be P1, this will be G1. Similarly it will be P2, it will be G2. Similarly it will be P3, it will be G3. Then it will be C out, C4, that is the C out. Then this is the C0, the input carry. This is the input carry. Then the output from this carry look ahead generator, the C1 comes to the second full adder. C2 comes to the third full adder. C3 comes to the fourth full adder. This is C3. Okay, C3, C2, C1 and C0. So this is the circuit of 4-bit carry look ahead generator. Okay, so here in this case the maximum delay for the carry look ahead adder will be 6 cross del. Here for GI and PI generation, the delay is del. Delay is equal to del. For carry generation, it will be 2 delay. Okay. For carry generation, for CI generation, delay 2 del, and for some bit it will be 3 del. For some bit SI it will be 3 del. So del is the average gate delay. Here del is the average gate delay. Okay, so the same holds good for any number of bits because the added delays does not depends on the size of the number. So it is independent of the number whether it will be n bit or whether it will be 2n bit or whether it will be 4 bit, like this. It is independent of number of bit. So this is all about the carry look ahead generator or and carry look ahead adder. So this is the circuit of 4-bit carry look ahead adder. Carry look ahead adder or CLA. This is the circuit. Okay. So now we will do the binary incrementer, binary decrementer. Now the binary incrementer circuit. So here the 4-bit I am drawing 4-bit binary incrementer circuit. Okay. So binary incrementer unit is used to perform the increment microoperation. The increment microoperation adds 1 to the number stored in the register. So here if we give the example of 4-bit register that has a binary value 1001, then after incrementing it, it will be 1010. So incrementing means basically 1 will be added. Then if 1010 is stored, after incrementing by 1, it will be 1011. That means 1 will be added with it. So the micro operation can be implemented by using either the some up counter or by the combinational circuit. So this is the combinational circuit for binary incrementer where we will use 4 adder circuit. Okay. So 4 adder will be connected and that means 4 adder will be connected and the output of the 1/2 adder will be the input of other. So here we are connecting only half adder. No need to connect the full adder. So here the half adder are connecting in cascade. So one input one of the inputs of the least significant bit half adder is logic 1. So in another cases only we need the carry input and one input. That is why full adder is not needed. In case of full adder, carry input and other two input are needed. But here as we required only one input except carry, that is why the circuit can be implemented by the using of half adder only. So the circuit can be extended in the n bit incrementer. So the half adder will be just cascaded, connected in cascade. Then if we want to implement n bit incrementer, n number of half adder will be connected. Okay, so instead of half adder, full adder also can be used. Then if we use the full adder, then other bits will be put at 0. So no need to use the full adder, as it will only increment the number of ICs or number of gates, logic gates in the circuit. So for that half adder is enough. So for n bit incrementer circuit, we have to use n bit half adder. So here I have basically drawn 4-bit incrementer where I have used incrementer, where I have used 4 half adder. Okay. So this is all about the half adder, all about the incrementer circuit with the help of half adder. Okay, so this is the incrementer circuit. Now we will do the decrementer circuit. So now the binary decrementer circuit, this binary decrementer circuit. In case of binary decrementer unit, it performs the decrement microoperation. So the decrement microoperation subtracts value 1 from the number stored in register. Suppose in 4-bit register that has a binary number 1010. So after the decrement operation, if decrement operation is being performed, then the number will be 1001. So it is decremented by 1. So the same operation, this operation can be easily implemented by the use of the combinational circuit of half subtractor or the sequential binary counter circuit. So these may occasions when the decrement microoperation must be realized with the combinational circuit of full adder also. So here suppose we are doing the 4-bit decrementer circuit. So here we are connecting 4 full adder. These are 4 full adder that will be connected in cascade. So here the output of one full adder will come to the input of the next full adder. So this is the Cin equal to 0. Okay. So this is A0, this is A1, this is A2, this is A3. Okay. So in full adder we will get sum and carry. So this is sum, carry, here we will get C4, here S3. Now in this full adder this is S, that is S2 basically. Then this is S, basically S1. This is S, it is basically S0. And this is C. So here we are adding a bit 1 as one of the input of the full adder. That means actually in case of decrementer circuit, we will add the 2's complement of 1. Here for decrementing, we will add 2's complement of 1. Okay, so 2's complement of 1 means nothing but 4, 1. This is the 2's complement of 1. So if we write 1 in 4 bit, the number will be 0001. So its 1's complement will be 1110. Its 2's complement will be 1111. As I have already mentioned that in case of subtraction, we normally add with 2's complement of that number. So if I want to subtract B from A, I will add with 2's complement of B with A. Okay, so here if I want to do 2's complement of 1, it will become 4, 1. Thus the binary number 1111 means minus 1 in decimal. Binary number 1111 means minus 1 in decimal. So since the negative number is represented in computer in sign 2's complement method, thus we are adding minus 1 with the operand and the resultant value we can store in register A. So this is all about the binary decrementer circuit. Now the 4-bit arithmetic adder subtractor. 4-bit arithmetic adder subtractor. So here if I draw one XOR gate and one input is 1, another input is A, what will be my output? It will be A complement. And if we give in XOR one input is 0, other input is A, it will be A. So here we can find these two property for two cases actually. In this case, if we give 0 and another input A, we are getting the same number. And if we give 1 and another input A, we can get just the complement of that. So the binary subtraction A minus B is equivalent to 2's complement of B is added with A. So the addition and subtraction can be combined in a single circuit using the exclusive OR. Suppose the condition of the carry in bit is 0, that means it will be addition because there is no change in the output with the input, and in case of subtraction we may use 1, the number itself is being changed with its complement. So when we will draw the circuit of the 4-bit adder subtractor, we need 4 XOR gate as well. So first of all we are drawing 4 full adder circuit, okay. This is 4 full adder circuit. So one input is A0, the LSB, A1, A2, then A3. This is one input. Another input B0, B1, B2, B3. So we will add A3, A2, A1, A0 with B3, B2, B1, B0 or A3. This is the in case of addition, or A3, A2, A1, A0 subtract B3, B2, B1, B0. So while addition we will use the XOR as 0 is one input and another input is the B input. So here actually this is the B input for XOR gate. So this is the output. This is B3. Okay, so this is B3. This is B3 and this is another input. Okay, so this is another input. Now I am just connecting the XOR gate here. This is one input. Similarly, XOR gate. This is one input. Similarly, the XOR gate. This is one input. So all the input, that is B1, B2, B1, B3. These are the input. And another input that is connected with this. Okay. So here basically actually this is another XOR. So here the one input is B0, B1, B2, B3 and another input is the carry in. This is the carry in, C in. So it can be either 0 or it can be 1 and the resultant will be the sum 0, sum 1, sum 2 and sum 3. And this is the C4. So here we can connect this. So here C1 will be connect with this. This is the C in. Then it is C1, it is C2, it is C3. So the here if we write this selection as the input, if we write this C in as selection input, if we write this as selection input, so it determines the operation, whether it will be the addition operation or whether it will be the subtraction operation. So when A is equal to selection input C in, that is equal to 0. C in is basically the selection. So here if the selection input is 0, then the circuit performs the addition operation. And if the selection input is 1, then the circuit performs the subtraction operation. So the input to each XOR gate are the one is the C in, that is the selection input, and another input is the B input. So if we write here B XOR the selection input. Okay, so B XOR the selection input, then it may be either B XOR 0 or B XOR 1. If it is B XOR 1, it is nothing but B complement. If it is B XOR 0, it is nothing but B. Okay, so after this, if we perform that the operation is A plus B, that means the addition simple as we have done in case of ripple carry adder. It is simple like the ripple carry adder. Similarly, in case of subtraction, it will be like the 2's complement addition. So this means that the circuit performs the addition of A with 2's complement of B for unsigned number. That means if A minus B operation it will do, where A if greater than B or the 2's complement of B minus A if A greater than B. So for signed number, the result is A minus B, provided that there is no overflow. Okay, so in this case, the subtraction is being done. So when if I give two numbers, suppose one number is 1 0 0 0, another number is also 1 0 1 0. So if the addition is being performed between these two, the result will be 1, this is 0, this is 1, 0. So C4 will be 1, S3 will be 0, S2 will be 0, S1 will be 1 and S0 will be 0. Then if we want to perform, this will be the case of Cin equal to 0 or selection line is selection equal to 0. So in case of selection equal to 1, when selection equal to 1 for the same number, it will be 1010 will be 2's complement. 2's complement of 1010 is nothing but 0 1 0, 1 is 1's complement, 0 1 1 0 will be 2's complement. That means 1000 will be added with 0110 and the resultant will be 0111. So this is the result of the in the case of A minus B. So actually we will get the output of the 2's complement of that. Okay, so basically what is the number? This is 10 and this is 8 in decimal. This is 8 and this is 10 in decimal. So when we perform that 8 minus 10, here we are doing just nothing but 8 minus 10. So if we get the 2's complement of these, we will get 0 0 1 0. That is the 2's that is actually 2. So how we are getting 2? By 2's complement of this result. So we have written that 2's complement of B minus A if A less than B. Here in this case, in our example, A is less than B. So this is the circuit of the 4-bit arithmetic adder subtractor. Okay, so today we have learned what is the serial adder, what is parallel adder, then what is carry look ahead adder. After that we have implemented the circuit of the binary incrementer and decrementer. So here what we have learned, in case of serial adder the circuit is so small, it is very expensive. The circuit needs only one full adder and one flip-flop, but the circuit takes n clock cycle for addition of n bit number. Similarly, in the case of full adder or ripple carry adder, it is cascaded. The output of the carry out of one full adder will be the input of another full adder. That means it is cascaded and it is ripple like water. So it is called the ripple carry adder. Carry is propagated from one full adder to another, and this adder being a combinational circuit is faster than serial adder. In one clock period, all bits of the two numbers are added, but the circuit becomes too large. So to avoid this, the carry look ahead adder is come into the scenario where the delay will be avoided and the output C out of the carry is dependent on only C0. It is not dependent on C1, C2, C3. By the help of the equation, we have already shown that. Then the binary incrementer circuit, incremented is nothing but the number is increased by 1. Similarly, in case of decremented circuit, the number is decremented by 1. Now, this circuit is 4-bit adder subtractor circuit. So, it is the combinational circuit where both the addition and subtraction can be performed. Okay. So, this is all about the arithmetic, different arithmetic circuit. Now, combining two different arithmetic circuit, we can make the 4-bit arithmetic unit that we will discuss later. Okay. So, up to this.